So this is MOSFET IV characteristics. So far we talked about the MOSFET structure. So it's just a capacitor structure. We haven't talked about the current flow in the MOSFET. So today we are going to discuss the current flow. And this is a reference chapter, and then the lectures by Professor Asif. So let's review what makes the current in the MOSFET. So here, this is a N-type MOSFET. So we have the P-type doping in the substrate. And then we apply gate voltage, positive gate voltage. As we discussed, first we are going to create the depletion. The holes are pushed away. So you have the Na minus there. And then we keep increasing the gate voltage to the threshold voltage. We will create this inversion of the electrons to the surface. So this is what we have discussed in the previous lecture. Now, if we apply the drain voltage, okay, the drain voltage is larger than 0, then we will have the current flow like this. So this is the source, this is the drain. If the Vd is larger than 0, because current, let's say electron will move from the source to the drain. The drain is higher voltage potential. Electron tend to move to higher voltage potential. So that's why the electron move in this loop. Of course, the current will flow from the drain to the source. Because the definition of the current is opposite to the electron flow. So, by the way, the MOSFET structure is symmetric. The left-hand side and the right-hand side actually looks identical, right? So, this suggests that it's not necessary the left-hand side is source, the right side is the drain. So, what determines the source and what determines the drain is the voltage you apply. So in this example, if we apply positive voltage to the left-hand side, then this left-hand side will become the drain. The reason here, this is the drain because we apply the drain voltage positive here, and this side is ground. But if we reverse the voltage polarity, then the source and the drain definition will also change. Okay, so this is the current flow in the MOSFET. In this NMOS, current flows from the drain to the source. Electron move from the source to the drain. This is above the threshold voltage, where you create this channel under the oxide. So this is the channel. Source and the drain, because N-type, there are many electrons. In the channel, there are also electrons. So then we have this electron flow from the source via the channel to the drain. So that's the current. Now we are going to derive the IV equation for the MOSFET, because we want to know how large is this current. So the current depends on the voltage you apply. So there are two voltages you apply here. One is the gate voltage Vg, one is the drain voltage, VD. So then the current is a function of those two voltages, and we need to derive this current as a function of those two voltages in the next. So in the previous lecture, what we discussed was the MOS structure, that band diagram. Actually only talk about this X direction, because we only have the MOS. But the current flow is to this Y direction in this case. So from the source to the drain. Let's say the electron flow is from the source to the drain. So we need to think about how to derive this current. First, we need to think about when we apply the drain voltage here. Because only when you apply the drain voltage, you will have the current. So if we apply drain voltage there, then this voltage VD, let's say, is applied to here. This is a contact. So let's say you have the voltage here, VD. So this voltage, we assume it will be linearly drop to 0, because on this side you ground it. So then the voltage is 0. So you have voltage drop along this channel from right to the left. The voltage drop is VD to 0. So this is the voltage across this channel. But we care about the voltage difference between the gate to the channel here. So what is the voltage difference here? And what is voltage difference here? So this is what we care about. And this is different because the voltage here, you are going to have the gate voltage Vg. But to this very left point, you are going to have the Vg across this MOS structure, right? Because this point is ground. You have Vg to the gate. So to the left point, boundary here, you have Vg across the MOS structure. But to the right boundary, this point, the voltage across this MOS is not Vg. Why is that? Because you have Vd here, the voltage potential is increased by Vd. So the actual difference of the voltage is this Vg minus Vd across the MOS structure. So this is different to the left, between the left and the right boundary. That means the electron density will be different between the left and the right boundary. So why is that? So the inversion, here we plot the inversion charge density here. It's negative charge, so we show the arrow down here. And then this charge at this point, it's like a plate capacitor. And then the plate capacitor tells you that the charge across this capacitor at this location is the capacitance times the voltage difference. And here we need to consider the threshold voltage, because only when the gate voltage is above the threshold voltage, then we have the inversion charge. So the effective voltage that is across this capacitor is Vg minus Vt. because we need to overcome Vt first to create the inversion charge, that's channel. So then the effective voltage across the capacitor is Vg minus Vt. And then multiplied by the COX, which is the unit capacitance. And then times W. So what is W? W is the, we need to consider this in a three-dimensional view. So W is the width of the transistor. So let's see. We don't have that in this lecture, but we have shown this before. If we look at this three-dimensional view. So here we have two parameters. One is called W. This W is different than that depletion width. Okay. This W is called the channel width, because here we have the channel, and then this is to the third dimension. So this is how wide your channel is. And then this L is the channel length or gate length. So that is the distance between the source and the drain. And the width is how wide your transistor is. So then of course the wider the transistor, the larger charge under the gate is proportional. So that's why here we multiply by the W. Okay, so then here we assume the drain voltage equals to 0. Then both source and drain is 0 in this initial condition. Then the charge density, the electron inversion charge density, will be uniform across the channel from the source to the drain. At the drain side is also the W times COX times Vg minus Vt. So this is the same. Now, to get the current flow, we need to create Vd larger than 0. So if Vd larger than 0, here we will see that the electron density to the drain side will be reduced. Why is that? Because here now the voltage across this capacitance will be smaller. So initially we have the gate voltage minus Vt, that is the effective voltage across this one. But now the other side, this plate, the voltage potential is raised up to the Vd. So the actual difference is Vg minus Vt minus Vd. Vg minus Vt minus Vd. That is the actual voltage difference, because now you have Vd here. So then the voltage difference is smaller, so the charge is smaller. So here you see that the charge becomes smaller when you have the Vd. And then next, when you further increase Vd, then you are going to reduce further charge at the right boundary here. So then let's derive the total number of charge in the channel. So we need to get the total number of charge in the channel. And since this is decaying from this to here, so we can use the middle as an average charge, because the charge is non-uniform here. But on average, you can think it's the left side plus the right side divided by 2. So you have the left-hand side charge, right-hand side charge, and then divided by 2. So that is the average charge in the channel. So let's get this average charge, Q average. So this average charge, if you do that, is the average of those 2 points, as we showed in the previous slide. If you do that, then it will become WCOX Vg minus Vt minus 1 minus half of Vd. The same equation here. From this equation to the next slide, this one is the same equation. So that is the average charge along the channel. Then the next step, we want to get the current, the string current, and we know what determines the current. How many charges in the channel and how fast they move, right? So this will determine the current. So how many charge in the channel? We already got the average charge density, Q average. Then how fast? Then is the velocity of the electron. And the velocity, this is due to the stream voltage, that is the drift current. So you know the drift current, you have that mobility multiplied by the electric field. Because the velocity equals to mobility times the electric field. And the electric field is from the stream to the source due to the VDS, due to the stream voltage. You have a horizontal field from the drain to the source because you have VD larger than 0 and your source is ground. So then we can plug in the Q average from the previous slide, which is this one. And then we plug in here and then multiply by mu n and E. So what is E? E is the horizontal electric field from the drain to the source. So that is Vd divided by L. L is the distance between the source and drain. That is the channel length. And by definition, you know, electric field is the voltage over that distance. So it will be this Vd divided by L. So you get this. And then you can rearrange this a little bit. Eventually, you will get the equation in this box. So that is the current for the MOSFET. So it's mu n. This is for NMOS. So you use mobility for electron. For PMOS, you're going to use mu p. So this is mu n COX W over L. This is the design parameter of the geometry. W, as we showed in the previous 3D cartoon figure, W is the width of the channel, L is the length of the channel. So W over L. And then here in this bracket, you have some voltage terms. So Vg minus Vt is gate voltage minus threshold voltage, then multiplied by drain voltage Vd, and minus half Vd squared. So you see here the current depends on both gate voltage and drain voltage. So this equation is very important. You are going to use this over and over in the rest of the semesters. Any questions? Again, I don't require the derivation of this one, but the final equation is very important. And you need to understand the current depends on the mobility, depends on the capacitance, depends on the geometry W over L, and depends on the voltage, gate voltage and drain voltage, VG and VD. So this is the linear region. We will discuss why it's called linear region in the next. But if we keep increasing the drain voltage, the transistor will enter so-called the saturation region. So this is what will happen. So you remember this charge density plot we have earlier? And then as we increase the drain voltage, we said that the charge density to the drain will decrease. However, if the drain voltage is not enough, this one will decrease to 0. Okay. So previously you see initially the charge density is like this. As you increase the drain voltage, this decrease, and then decrease, and then eventually becomes 0. So this is called pinch-off condition. The channel is pinched off at this moment. So the condition for the pinch-off is when this charge to the drain side becomes 0. So that means this one becomes 0. If this one becomes 0, you will get the condition where the Vd equals to Vg minus Vt. So this is condition for the pinch-off. And after this, the transistor will enter the saturation region where the current will no longer increase. So this condition will also give you the Vd set, is the saturation drain voltage. So above the Vd set, if you further increase the drain voltage, because here the charge becomes 0, so then the current will no longer increase. So whatever charge you have in the channel will quickly be swept to the drain, and then you don't have the current increase anymore. So if you plug in this condition, this Vd set equals to Vg minus Vt into the previous equation. So let's say you get this Vd set